In this video, we want to do some review questions to bring together all the concepts that we have learnt so far throughout this playlist. So starting with our first example, we have the unit circle here with the coordinate PQ, and we first want to find sine of 228 degrees in terms of P and Q. So the first logical step would be to try visualize our angle of 228 degrees on the unit circle. So starting on the positive x-axis where 0 degrees is, we're going to go around 180 degrees. And it turns out if we go 48 degrees more, we will get to our angle of 228 degrees. And so let's mark in a rough sketch of what this may look like. And this angle here will be 48 degrees, where if we go around 180 plus 48, that gives us 228 degrees. Now, if we consider these two angles on the unit circle as right triangles, you'll find that they are the exact same triangle, just reflected over the x-axis. And this is because, well, all the angles are going to be the same. We'll have 48 degrees, a 90-degree angle, and whatever's left over. And also, at least one of the sides we can see are the same, being these two hypotenuse sides, where they are both the radius of the unit circle, and by definition we know that this will be of length 1. Now that we have found a relationship between our two angles, we can start to find what our coordinates will be in terms of P and Q of our angle of 228 degrees. And this is going to be related to our coordinates in our second quadrant. And the way we're going to find our x component for 228 degrees is by considering that the two bases of our triangles will be the same length, and our base is related to our x component of this coordinate here. And so our base for our angle of 228 degrees will actually be the exact same x component, because if we map this down, this value here will be the x component P, and if we go further down, it will map to the same value. So we have our x component at 228 degrees being P. And now to find our y component, well, this is related to the height of our triangle, as these two heights are going to be the same. And we know that the height is going to be our y component at our coordinate, which is Q. And so this value that we read off the y-axis will be Q. And if we reflect this into the triangle in the third quadrant, we will have a length Q, but because we're reading off the negative axis, this value will actually be negative Q. And so our y component at our angle of 228 degrees will be negative Q. Now that we have successfully found our coordinates at our angle of 228 degrees, we can use our simple understanding of the unit circle to answer the question. So because we're trying to find sine of 228 degrees, this will just be the y component, which is going to equal negative Q. And similarly, if we want to find cos of 228 degrees, well, this is going to be the x component, which is going to be P. And finally, if we want to find tan of 228 degrees, this will be sine of 228 divided by cosine of 228, which is going to be negative Q divided by P. The next part of our problem requires us to find what tan of 48 degrees is. So first, let's try visualize this on the unit circle. So our angle of 48 degrees will be in the first quadrant. And so doing a rough sketch, it'll be an angle about here. And now for similar reasons as before, our triangle in our first quadrant is exactly the same as our triangle in our second quadrant, just reflected over the y-axis. And so we're going to have a relationship between our coordinates in our second quadrant and this angle here. So starting with our x component, well, our x component in our second quadrant is P, but because we're going to reflect this into the positive x-axis from the negative x-axis, we're going to actually have a value of negative P. And you can see that the height is going to be Q. And if we reflect this into the first quadrant, you can see that we're still reading off the positive y-axis. And so our y component stays the same as Q. So now we can find our value for tan of 48 degrees, and this will be, well, sine of 48 divided by cosine of 48, and sine, remember, is our y component, so it'll be q, and our x component will be our cos of 48 degrees, and that is negative p. So our value for tan of 48 degrees will be negative q over p. So that concludes our first problem, and now let's move on to our next one. For our next example, we want to show how cos of 120 degrees is equal to negative a half using only unit circles and geometry. So I've got the unit circle here, and the best place to start will be to draw an angle of 120 degrees in. So this will be in the second quadrant, and let's say it'll be an angle around here. And so this angle is going to be our 120 degree angle. We can also fill in some information, so we know that this length here is going to be 1, being the radius of the unit circle, and the angle here must be 60 degrees, as 120 plus 60 will get us to our 180 degree angle. And now let's make this into a right triangle and see what we can achieve. From our understanding of the unit circle, we know that cos is always read off the x-axis, as it is the x component of our coordinate on the circumference of the unit circle. And so if we are able to find the base, this length here, on our triangle that we have created, and we'll label it as x, we will be able to find what cos of our angle 120 degrees is. So let's draw this triangle to the side and see if we can use any geometric techniques to find what our value of x is. So to the side, I've redrawn this triangle here, the right triangle, and we are going to attempt to find our length x here. So what I've done is drawn a dashed line that represents this same triangle, just reflected over this height here. And so let's fill in the information that we do know. So if we reflect the angle to the other side, this angle here must be 60. And this side, the hypotenuse, must be 1. And also our base here is going to be of length x, as this is length x. We can also fill in our missing angle. So because we have a 90 degree and a 60 degree angle, and that the sum of the angles must add up to 180 degrees, the angle here must be 30 degrees. And reflecting that over, this angle must also be 30 degrees. Now what we're going to do is combine both triangles together and try to find some results. So let's draw this to the side to keep everything neat. And let's fill in the information. So we know that this angle here is 60. And this angle is also 60. And the angle up here, well, it's going to be 30 plus 30, so it will also be 60. And our two sides here are both 1. And finally, we have our x here and another x, so we have the base of this triangle as 2x. Now I hope you can see that we have an equilateral triangle here, and by definition all the sides of an equilateral triangle are equal. And so because we have one side equal to 1 and another side equal to 2x, we can equate these and we have an equation that we can solve for x. So we'll get 2x equals 1, and if we solve for x, we know that x must equal a half. At the moment, we have shown that this x value, the distance here, is equal to a half. And now we just need to relate this to the context of the unit circle. And so if we know the distance of this base of the triangle is equal to a half, that means that if we start from 0 and we go left a half units, then we get to the coordinate or the x component of negative a half. And we know that cos is always read off the x-axis, so this concludes that cos of our angle, in this case 120 degrees, must be this x component of negative a half. That completes this problem, and now let's move on to another one. For our next question, we want to find the values of x between 0 and 180 degrees, where tan of 3x is equal to 0.6. And we're also given the information that tan of 31 degrees equals 0.6. And because we have something associated with the angle in tan of 3x, we are going to make a dummy variable, which we have done before. So our dummy variable here is going to be theta, and we're going to let theta equal the angle. And the angle in this case is 3x. And now that we've made a dummy variable, we have to change the domain of our question. And so if theta is 3 times x, then the domain of theta must be 3 times the domain of x. And if our domain for x is between 0 and 180 degrees, well, 0 times 3 is going to give us 0, and 180 degrees times 3 is going to get us to 540 degrees. And so now we have everything laid out to sub in our question in terms of theta. And so we have tan of 3x, which in this case is theta now, is equal to 0.6. And we want to find all the values of theta now between 0 and 540 degrees. And once we found these solutions, we can sub in our dummy variable back in and eventually solve for x. So now let's draw the unit circle and try to find these solutions for theta. We have the unit circle here, and let's first fill in our domain. So our domain is between 0 and 540 degrees. So that means we're going to have to do one whole revolution around the unit circle. And we have to go from 360 another 180 degrees more to 540. So we're going to do another half revolution and end up on the negative x-axis. And we know that tan is always read off the y-axis, and in this case it is equal to 0.6. So what we're going to do is find 0.6 on the y-axis, and that's going to be about over here. And we're going to extend this out to touch our x equals 1 line, where we can finally fill in our angles that correspond to this equation tan of theta equals 0.6. So we're going to have two angles by extending our line to touch this coordinate. And there'll also be another angle in our third quadrant, because when we extend this angle out to touch the x equals 1 line, it'll give us a y component of 0.6 also. There was also another piece of information that the question gave us, and that was that tan of 31 degrees gives us 0.6. And so this angle in the first quadrant must be 31 degrees. And now that we have found our angle in our first quadrant, we can finally solve for all our angles of theta. So theta, our first angle, will be this 31 degrees. And to get our next angle in the third quadrant, well, that's going to be from 180 degrees. We're going to add 31 degrees to get to this angle. And so we get an angle of 211 degrees. And remember, we have to do one more half revolution to finish our domain. And so we're going to have this last angle past 360 degrees, which is going to be 360 plus 31 to get to this angle. And that gives us an angle of 391 degrees. At the moment, we have solved for all of our values of theta within our domain, but the question asked us to find all the x values. So we have to sub in our dummy variable back in, and we know that theta is equal to 3x. So all these solutions are equal to 3x. And so if we divide 3 to every our value of theta, we should get all our solutions of x. And so we get x is equal to, well, 31 divided by 3 will get us 10.3 degrees. 211 divided by 3 will be 70.3 degrees. And finally, our 391 degrees divided by 3 will be 130.3 degrees. And so these are our solutions for x. So that concludes this example, and now let's move on to our final problem. For our final problem, we want to find the two smallest positive solutions for the given equation. So let's rewrite this equation. We have the square root of 2 times cos of x over 2, take 60 degrees, is equal to 1. And now the first step is always to rearrange the equation. So we can take the root 2 over to the other side. So let's do that. We get cos of x over 2 take 60 degrees is equal to 1 divided by the square root of 2. And to leave the right hand side as simple as possible, let's rationalize the denominator. So this can occur by timesing and dividing by the square root of 2. And so the square root of 2 times 1 is going to give us root 2. And the square root of 2 times the square root of 2, well, that's going to be the square root of 2 squared, and the square roots cancel out. So it's just leaving us with 2. Now notice that once again we have something associated with the angle, and so we're going to make a dummy variable. So let's let theta equal to this angle, which is x over 2 take 60 degrees. And the next step will usually be to find the domain of theta, but because this equation looks quite difficult, I'm going to leave this step out and try a guess and check method, which you're going to see later on. So for now, let's just continue the problem as usual, but without finding the domain of theta. And so we get cos of this result here, which is now theta, is equal to root 2 on 2. And now we can just draw up the unit circle to try visualize this result. We have the unit circle here, and because we're dealing with cosine, we're going to be reading values off the x-axis. And let's mark in our value of root 2 on 2. So say that that value is somewhere here, and that's going to correspond to two angles, one in the first and one in the fourth quadrant. And let's fill in what these angles will be. So we'll have our angle in the first quadrant here, and our angle in our fourth quadrant, here. And remember, this value on the x-axis is read as root 2 on 2. Now we can use the Masterly table to find what our value will be in the first quadrant. So because we're dealing with cosine, we're going to go along the cos row and look for root 2 on 2, which is going to be along this column here, as we have the root 2 on 2. And this corresponds to an angle of 45 degrees. So this angle in the first quadrant must be 45 degrees. Now we have all the resources to find some values of theta, but notice that we don't have a domain filled in, and so we don't know how many solutions of theta to find. But what we're trying to do is find a good range of values for theta, so when we solve for x, we have the transition from negative x values to positive x values, and we can just pick out the two smallest positive x values. So we can start by filling in our value of theta in the first quadrant, which is 45 degrees. And we're going to get some negative values just to get a good range. So going right or clockwise around the unit circle, we get to negative 45 degrees. So we have plus and take 45 degrees as two solutions so far. And to get our value in the third quadrant going around, this will be 360 degrees, take 45, and that gets us to 315 degrees. And we're also going to get the negative value. So if we go around to negative 180, negative 270 to this angle here, we're going to have negative 360 and we're going to go anti-clockwise, so we're going to add 45 degrees, and this angle here will be negative 315 degrees. And so we're going to have both the positive and negative value of 315 degrees. And so we got 2 positive and 2 negative solutions for theta, and hopefully this is enough to get a good range of x values. So let's solve for x. In order to solve for x, we have to rearrange our equation here. So let's first take 60 over to the other side, and we get x divided by 2 equals theta plus 60 degrees. And we can multiply 2 to the other side to isolate x, and we get x is equal to 2 times theta plus 60 degrees. And so if we sub in our 4 angles of theta, we're going to get our solutions for x using this equation. Now let's solve for our values of x, starting with our most negative value of theta, which is negative 315 degrees. And so x is going to equal 2 times theta, which is negative 315, plus 60. And if we solve this on our calculator, we get negative 510 degrees. So our first solution is going to be negative 510. And if we do a similar thing for all our other angles of theta by subbing it into this equation that we've made, we will get 30 degrees, 210 degrees, and 750 degrees for our values of x. And you can see that we have a good range of values for x, where we start from negative values and we go to some positive values. And because the question asks for our 2 smallest positive solutions of x, we can only consider our 30-degree angle and 210-degree angle for our solution. So that's the end of our last problem, and that concludes this playlist on solving trigonometric equations.